Hello, welcome to the 7th video that I'll be making, which will be on dry etch, which is basically plasma etch, etching in a plasma environment. So maybe first I'll start out with a non-technical summary. So this whole idea of etch is a bit like, you can think of it like digging a trench in the ground, right? You want to dig where you want to dig, and there are certain areas where maybe you want to leave it untouched for construction or for paving a road on it, but you want to dig this trench down maybe so that you can lay down some cables or lay down some piping. So it's the same idea in semiconductor engineering, where you actually want to etch certain features into your semiconductor material while leaving other areas of the semiconductor material untouched. Okay, so it's areas where you do not want it to be etched. And so in dry etch, right? In dry etch, the main etching environment is that of a plasma. So this is different from wet etch, where the environment was an aqueous solution. So now in this case, we have a low pressure gaseous plasma that is can consist of different kinds of gases. Okay, and so to achieve this environment and to achieve this etching, so there exist specialized machines, right, dry etch machines, right, sold by vendors such as Tokyo Electron, among other companies such as Lam Research and so on. Okay, so let's go into the technical content right now. So in dry etching, normally dry etching is thought of as more of a directional etching. Okay, so directional etching is provided by the acceleration of ions that are heating and bombarding the wafer. So in dry etching, both neutral species and radicals may be involved, and we need to take note that any byproducts formed during this etching process should be volatile, right? So they should be in the gaseous state, right, under the deposition conditions, so that it will not fall back on the wafer. So imagine if your byproduct was solid, right? So you remove the material, but the material that you remove is in a solid form. It can splatter onto other parts of your wafer, it can fall back into the trench that you're trying to etch, and things like that. And so we want basically dry etching is able to achieve a more stable process control compared to wet etching, because you can control things like the ion energy, the plasma energy, right, the contents of your of a gaseous composition of your plasma and things like that. So it's able to achieve a greater controllability of the process. And what dry etching is able to achieve is that it's able to achieve a high aspect ratio. High aspect ratio refers to the depth to your width ratio. So you can achieve deeper and narrower trenches compared to wet etching, because wet etching, what you normally have is an undercut kind of phenomenon, right, due to the isotropic nature of wet etch. Okay? And so in the actual semiconductor fab, there's implementation of things like automation, endpoint detection, automated control of the etch process, etc. So endpoint detection is, for example, there can be ways in which the machine can detect when to stop the etch. Maybe like you can tune it such that I stop the etch once the bottom layer, a certain layer, is exposed. Right? And so how do they know that the layer is exposed? There can be various ways such as spectroscopy and things like that. Okay. So this is roughly how a plasma etching machine looks like. I'll show you a more detailed diagram later when I cover the various forms of plasma. But basically the idea is that you have a plasma that is like next to your wafer, and inside the plasma we are pumping certain gases, so depending on what is your etching chemistry that you want to implement. And so there's certain bias, so most of the time it's a radio frequency, so it's an alternating bias, electric bias, to generate and maintain this plasma. And normally at the back of your wafer there's like a cooling system, right, to prevent your wafer getting too hot during your etching process. Okay, so what is plasma? Plasma, some people call it the fourth state of matter, but basically it's the idea is that when you apply a very strong electric field, right, normally it's application of a strong electric field, although it can also be through like laser irradiation. But let's say you apply a very strong electric field and a gas starts to become electrically conductive, right? Originally non-conductive gas, right? Normally gases are non-conductive, right? Starts to become electrically conductive. And why? That's because the molecules or atoms in the gas, right, start to break down into charged species, into ions and electrons. Okay, so initially, let's say initially, uh, only a bit of current, right? When you apply electric field, right, only a bit of current starts to flow through your gas, right? Because the gas is non-conductive in nature. Okay, And then, however, they reach a point, right? So when there's a small amount of current that flows through, right, your voltage keep rising because it's a electrical insulator kind of behavior. However, there reaches a point, right? We can call this a breakdown voltage, where the voltage sharply drops, right? This indicates a large decrease in the resistance, or a large increase in the conductivity of the gas, and this right, represents the beginning of the formation of the plasma. When ions are generated in the gas, right, these ions can help with the conduction of electricity. Thus, we see a great drop in the resistance and the resistivity of this gas, and we say that the plasma has been formed. So normally, like when you do your plasma etching, or later you'll see the plasma kind of deposition methods, we basically operate in the regime of a plasma. However, if you, like, let's say, apply even stronger electric field, further concentrate and strengthen the electric field that's being applied to your plasma, eventually we observe something called arcing, right? Arcing, where like basically it's a bit like lightning. Lightning is an example of an arc, where high current density, right? High current densities can flow through specified paths where the conductivity of electricity along those paths are greatly enhanced. Okay, so what is inside plasma, right? So as we mentioned just now, there are charged species that can act as ways to conduct the electricity. So there's electrons and positive ions. However, right, there can also exist radicals. So let's say your original gas is carbon tetrafluoride, okay, CF4. So the ionization process can involve breaking up into ions and then release of electrons, right, to maintain charge neutrality. However, it can also, right, there can also be dissociation. So let's say a high energy electron in the plasma bombards a neutral CF4 molecule, and it breaks up into two neutral radicals, right, CF3 and your F, your fluorine radical. And in addition, also there can also be excited species. In fact, there will be excited species. So when the electron bombards a CF4 molecule in the ground state, it can be excited to a higher energy state, and afterwards this excited molecule can de-excite back to the ground state, releasing, right, light, releasing a photon of light. And so this is why plasma, right, we observe that plasma normally glows, right. It can glow strongly or it can glow weakly, right, depending on the energy and density of the plasma. But normally the plasma we observe to glow, and this is the reason why it glows, right, because excited species in the plasma de-excite and release photons of light, right? Okay. And yep, so in weakly ionized plasma, which is normally the case that we see in our machines, plasma etch machines, right? So we have basically electrons that have very much higher temperatures, very much higher energies than the ions, right? And this is because the electrons are lighter in mass and is basically more able to be accelerated by the electric field that we are imposing on the plasma. And however, there also exist ions with relatively high energies, and these bombarding ions, right, impact onto the substrate, which is our wafer, our semiconductor wafer, and that drives the plasma etching process. Okay, so one way to generate a plasma is through a DC bias. Okay, you can say a direct kind of electric field. So this electric field is a constant value, or let's say it may not be constant, but basically it does not alternate in direction. Okay, it does not alternate in direction, it does not alternate in sign. So the main mechanism by which the plasma is maintained under a DC bias is this generation of secondary electrons. So when there is a bias being applied, right, let's say a negative bias is applied here, and here is connected to ground. So when the negative bias is applied on the cathode, right, the positively charged ions, right, that obviously exist in your plasma will be accelerated towards this cathode, and it will bombard on the cathode, and when it bombard on the cathode, it tends to release secondary electrons, and these secondary electrons will be accelerated in the opposite direction, right, by the electric field because it is negatively charged, and they will enter into, right, the encounter rather the let's say uncharged argon atoms in your plasma, and this can lead to ionization of these argon atoms when this electron bombards the argon atoms, thus producing argon ion, as well as more electrons that can further drive the maintenance of this plasma. And this ion can once again be attracted to the cathode, bombard the cathode, release a secondary electron, and therefore the plasma is maintained, right, by this DC bias. And so what we normally observe is that when the plasma is formed in the metal chamber, this plasma does not fill up the entire space, but there's a sheath that surrounds it. So on the left and on the right, there's like a dark zone. Okay, it's a dark zone. So what is the reason for this? Actually, it's very simple. This is because, right, both ions and electrons will basically be accelerated uh, towards the electrodes, right, towards the electrodes. And this creates basically uh, ion current and an electron current that flows to the electrodes. However, the thing is that, as previously mentioned, right, the electrons are very much smaller in mass. The electrons are very much smaller in mass, and so that's why um, the electron current will tend to be much higher than the ion current initially. Okay, and so in order to maintain the stability of the plasma, so the plasma region needs to be at a higher potential so that the ion flux, the ion current and the electron current is able to eventually balance out. So maybe another way that we can think of it that is maybe more intuitive to you is that the idea is that electrons leave the plasma at a higher rate than ions leave the plasma, right? Because the electrons have a much higher speed due to its smaller mass. So when electrons leave the plasma at a much higher rate than ions leave the plasma, naturally the plasma be raised to a more positive potential, so raised to a higher, more positive potential. Okay, so that is the reason why the plasma region is at a higher potential than the electrons. Okay, and another way to think of it is that when the plasma is raised to a higher potential, it will retard the electron current and enhance the ion current, thus allowing for a balancing of the electron and ion current to reach a steady state equilibrium level. Okay, yeah. So the reason why there's this shift, right, then is because near the electrodes, right, so when the plasma is raised in potential and the electrodes are now lower in potential, so there's an electric field near the electrodes now. There's an electric field near the electrodes, and this will accelerate any ions or electrons that enter into this region, sweep it to the electrodes. So you can think of these regions as being very, not having a low density of like of your species, of your ions and your electrons. And remember, why your plasma glows is when your electrons interact with your molecules to excite them, right, into higher energy state. So when in the shift region, there's basically a low concentration of electrons and ions, because these electrons and ions are swept to the electrodes, right? Since there's a low concentration there, there will also be a low incidence of the excitation events that occur in this shift, and therefore this shift will not glow. It will not glow. It will appear as a dark shift. Okay. So how about the RF plasma? Right? How about the case where you excite your plasma not with a DC bias, a DC potential, right, a DC bias over here, but with a radio frequency, so it's like alternating. So it's like a sine wave. You can alternate in both the positive and the negative potential, right? So the polarity swaps, right, every half a cycle. So what is the difference? How is the plasma generated and maintained in the case of a RF plasma? So it's different from the DC plasma case. In the DC plasma case, the plasma is generated and maintained by these secondary electron emission events, right? When the ions bombard onto the electrode and the secondary electrons are emitted. However, in the case of a RF plasma, right, this is a different situation where the plasma is maintained by the electrons oscillating near the electrodes, okay, near the sheath, right? Because when your applied potential is oscillating, right, the plasma that is near the electrodes will experience a oscillating electric field as well. And so electrons in that region will also follow the oscillating electric field and undergo an oscillatory motion. And when it undergoes an oscillatory motion, it can be excited to high instantaneous velocities. And when these electrons are undergoing high instantaneous velocities, right, high velocity motion, they can easily interact with the other species in your plasma, especially your neutral species, to generate more electrons, more ions, more excited species and all that, and thus maintain the state of the plasma. Okay. And so for the case of RF plasma symmetric electrodes, here we see a graph, right? That the potential, this is the potential graph, the potential of the plasma is higher than the potential at the two electrons, right? And that is exactly for the reason mentioned earlier. So even though this diagram shows the case of a DC bias, in the case of a RF bias, right, it's the same phenomenon. We see that the plasma is raised to a higher potential relative to your electrodes, right? In order to balance the electron and ion flux flowing to the electrodes. And so we actually notice something interesting over here, right? We notice that there is an electric field, right? There's a potential drop at the electrodes, even though there's no DC bias. We only have a RF bias that has basically time averaged voltage, time average potential of 0 volts, right? Because if you do a time average of the positive and negative positive and negative alternation, right, you get a time average of 0. However, there still exists, right, electric field, a potential drop at the electrode surface, and that's very important because when we do etch, right, we want to accelerate your ions near the wafer so that they bombard the wafer. And how do we accelerate the ions at the wafer? We have to accelerate the ions at the wafer through an electric field, right? An electric field that acts on these charged ions to accelerate them. Okay, so this is a very important phenomenon, and this is why it allows this kind of plasma etch to occur even with a RF bias. And so precisely for that reason, right, we developed, or rather equipment manufacturers developed this idea of this RF plasma with asymmetric electrodes, right? Why asymmetric electrodes? Because of the principle where you want to enhance the electric field experienced by the ions at the wafer surface, right? Because we want more ions to bombard the wafer so that it can etch the wafer. We don't quite care about the other electrode. The other electrode, in the case of a plasma etch machine, is a counter electrode. Right? It has to be there, right, as a counter electrode, right? However, it's not what we want to etch. We want to etch the wafer. So we want basically the self-established DC bias. So this is not an applied DC bias, but a self-established DC bias. We want it to be stronger at the wafer surface, at the wafer electrode, right? The electrode where the wafer is placed on. And so we apply this idea that the current flowing to the cathode and the current flowing to the anode, or basically the current flowing to both electrodes, right? The current flowing to both electrodes must be the same. The total current flowing through both electrodes must be the same. And so if, right, the electrode where the wafer is placed on is smaller, then the current density must increase because the same current must flow through a smaller area. Right, the same current must flow through a smaller area. So the current density will increase. And so what does that mean? That means that the current density is provided by ion bombardment as well, right? Ionic contribution to the total current. And so that means that when the current density at the wafer side is increased, more ions rather per unit area is bombarding the wafer. Okay? More ions per unit area is bombarding the wafer. And what we also observe a larger DC bias on the side of the wafer. So a larger self-imposed, self-generated DC bias at the wafer side. Okay? So this means that at the wafer side, right, there's a higher ion current, right, current density, and the ions are being accelerated to higher speeds at the wafer side. Okay? Right, and so that's why we place our wafer for ion assisted etching, for plasma etching, always on the smaller electrode. And so we see that the potential graph is something like this. The plasma has a higher potential, and then at the electrode where we place our wafer, there's a large potential gradient. And large potential gradient, of course, you know that it means a large electric field. Okay, so now let me cover more on the mechanisms, right? So we covered already the idea of a plasma and the idea of how the architecture of a plasma etch machine, right, follows the principles of plasma generation and potentials of the plasma, things like that. So now we focus on plasma etching mechanism. So there are 4 main mechanisms, right, general categories, right, of plasma etching. Right, the first one is a chemical etching. So in this case, there's no ion bombardment. There's no ion bombardment. So just now we talk about ion bombardment, but for the case of chemical etching mode, we stop the ion bombardment. We have a way to ensure that, let's say, there's a very minimal ion bombardment. And so what is happening is that your gaseous species that you put in your plasma, your radicals, some of your neutral reactive gases, undergoes a simple chemical reaction with your substrate, your semiconductor material, or let's say whatever film that you're trying to etch. Right? So it undergoes a chemical reaction and produces a byproduct. So the problem with this is that it's quite similar to wet etch, except now that the environment is not aqueous, but it's a plasma, it's like a gaseous plasma environment. But it's quite similar in the sense that there is no anisotropy. right? In the end, we get the isotropic etch. The etch is more or less equal in all directions. Okay, so this is sometimes desirable, sometimes not desirable. Okay, and so there's the second kind of etch is completely different. It's physical etching. So there's no chemistry going on. What all that we are doing is to accelerate high energy inert ions. So for example, Ar plus, right, argon ions, right, inert ions are accelerated to the material, and the material is dug out of the wafer, right? The trench is being dug out purely by this collision, purely by the energy of collision bombardment. Okay, purely by this kind of kinetic energy transfer. Okay, and so the problem is that, right, there's no chemical reaction. Your byproduct is the same material. Your byproduct is the same material. So it will still be a solid. It will not be like a volatile byproduct. So it can be spattered all over the place. So it tends to be dirty. It tends to be dirty, and also it's not selective because, as I mentioned in the previous video, in this case it's like shooting a cannonball at the wall. I don't care if your wall is made out of bricks, made out of concrete, or made out of wood. If your cannonball is fast enough, it can demolish all three walls, right? So it has less selectivity. Okay, as long as the ion energy, right, is high enough, right, almost any material can be spattered, right, and many materials spattered at similar rates also. So there's not much selectivity that we can see here. So that's why the third method is actually the method that is actually used, which is ion enhanced etching, also known as reactive ion etching. So we have ion bombardment, but this ion bombardment is not the main means by which a material is etched. It just activates the area. So you can think of it as like shining a light on the area to activate it, right? So it is analogously we shine the ions at a certain area to activate the area for the chemical etching to occur. So the areas where the ions, right, shine on are the areas where the reaction with your radicals and neutral reactive gases happen at the fastest rate. So we can define where you want to etch. So it's very anisotropic etch. And at the same time, it's also selective, right? Because the main mechanism of etch is still chemical in nature. So you can have your ion shine on another film that's not selective to the kind of etching chemistry, and it will still not be etched, right? So I hope you can see later. I'll go through a bit more. Hope you can see how it is both anisotropic and selective. And so the third kind is more like a modified version of the last kind rather is more of a modified version of the third kind of etching, as there's ion enhanced inhibitor etching. So we include a certain inhibitor that can coat the walls of the trench you're etching to ensure that we get very very high aspect ratio trench, very vertical trenches that just go vertically downwards. Okay, so we'll cover that later. So the idea of purely physical etching, as previously mentioned, is just using an inert gas as a plasma. Right, so plasma is of course an ionized form of gas. So we use a gas that is inert, like argon. Okay, so this is also known as ion milling or sputtering. Okay, so purely the mechanism is by your kinetic energy transfer. Okay, kinetic energy transfer. Your incoming inert ions knock out the atoms in your lattice of the material that you're etching. Okay, so yeah, so it's a post activity since many materials sputter at similar rates. Okay, and at the same time it can also cause damage to the surface, and it can make the process may be dirty because it may be re-sputtering. So the material you bombard out fall on other places of your wafer because it's not chemically changed. It was a solid, it still is a solid, right? So you can think of it like if you drill a hole in the wall, right, all your what's that called, plaster dust, right, or your dust from your concrete or your plaster, it will drop somewhere, right, drop somewhere. In the case where it's a vertical wall, it drop on the floor lah, but your wafer is horizontal, so it can drop other places on the same flat wafer, so that's not good. Okay, so however, for purely chemical etching, right, as previously mentioned, right, it's purely a chemical process. So often case, right, is your radicals, right, that are undergoing this etch process, because if you learned your chemistry well, you will know that radicals are generally more reactive, much more reactive, much more easily to undergo chemical reactions. So for example, fluorine radicals is well known that they are very good in undergoing chemical reaction with silicon to form SiF4, which is a gaseous product. So this product will just diffuse away presumably, and therefore your silicon is able to be removed by chemical etching. However, because in this case there's no ion bombardment, right, we do it in such a way where the wafer, for example, is not placed on an electrode, so there's no electric field on the wafer surface across the wafer, right? So the result is that there's no ion bombardment, so purely there's radicals arriving on the wafer surface, right, and undergoing a chemical reaction. Okay, and so this is also used sometimes, right, in the semiconductor industry, right. Normally it's called etching process. One way to do it, one way in which it is used is to remove photoresist. So the wafer consisting of the photoresist layer on it that you want to remove is immersed in a oxygen plasma, right? So it's not placed on an electrode, so there's no bias on it, no ion bombardment, and so the oxygen radicals in your oxygen plasma undergoes a oxidation reaction with your organic photoresist. Remember, your photoresist is an organic compound and basically forms your CO2 and H2O. Okay, so let's cover a bit of etching chemistries, right? So etching chemistries for silicon, we like to use fluorine because SiF4 is a volatile species with a very low boiling point, right? If you see chlorine is less desirable and so on and so forth, but maybe chlorine still can be used, but bromine is quite difficult to be used because it's not silicon bromide is not a very volatile species, right? High boiling point. Okay, for carbon we can also use fluoride, right? Right, or organic compounds you can normally use O2. Okay, germanium also you can use fluorine. Okay, however we realize that for certain species, right, for aluminium, right, you can use chlorine, bromine, because these are still somewhat volatile, so it's still somewhat low boiling point, right? LCl3, AlBr3, right? So we can still use chlorine and bromine based chemistries. However, if you see copper, right, right, all of these, right, chloride, bromide, all of the copper halides, they have a very high boiling point and they're effectively not volatile. So that's why when we change, right, the metal layers, right, there's basically in the past few decades there's been a change from using aluminum to copper as your metal of choice in semiconductor wafers, right. However, the main problem with that is that while previously we could use plasma etch using fluorine based chemistries for chlorine based chemistries, for example, to etch aluminum, right, now we cannot use chlorine based chemistries to etch copper. Copper cannot be easily etched using plasma etching, right? Because your products are not volatile, they are solid still, they'll fall on other parts of your wafer and contaminate other parts of the wafer, right? So this is very interesting. So how do we etch copper? How do we tell the copper, in a sense, tell the copper or tell the machine, right, where to put the copper and where not to put the copper, and when you put the copper, how to remove the copper, right? There's this idea of a Damascene process, which I think I've covered, right, in the second video on the overall microfabrication workflow, but I think I'll also cover again in maybe slightly more detail in the chemical mechanical polishing video. Okay, so finally we are going to this idea of the ion assisted etching, also known as a reactive ion etching. So this is a bit of a misleading phrase because it's not the ions itself that are reactive, but more like there's a reactive species and it's ion enhanced. Okay, so this kind of reactive ion etching process, right, actually kind of basically it focuses on the fact that etching, right, chemical etching, right, occurs at a much higher rate when a surface is exposed to ion bombardment. Yeah, so it exploits that fact, right. So as you can see over here, right, normal chemical etching has maybe a 0.5 nanometer per minute etch rate, but when the area is bombarded by argon ions, right, and so these argon ions are inert, they don't participate in the chemical reaction, but when the surface is bombarded by argon ions nonetheless, right, there's a 10 times increase, more than 10 times increase in the etch rate to maybe about 6 or even 7 nanometers per minute. Okay, and so this idea is basically exploited in this reactive ion etching. So we put the wafer on an electrode, right, on the electrode where there's ion bombardment, right, the smaller electrode where there's a high ion bombardment, and when the ion bombards on the surface of the wafer, that is where, right, the reaction between, let's say, your radicals, so let's say your F radicals, your fluorine radicals, and your, let's say, your silicon, right, that's where the reaction happens, right. Okay, so selectivity is good because you are still relying on the chemical process to do the etch. So for silicon, you're still relying on the chemical reaction Si plus 4F give you SiF4, right? However, we can also achieve very good anisotropy because the ion bombardment, right, comes down vertically. If you control your process parameters well, the ion bombardment should go down vertically. And when it goes down vertically, it bombards the bottom surface of your trench and not the sides, right? If you control it well. Okay, so it bombards the bottom surface of your trench. So the etching can be more vertically downwards, and so we call this better anisotropy, better anisotropy. Okay, so this is not like your purely chemical etch where the etch can happen, uniformly along all surfaces, but no, it's only surfaces bombarded by ions where the etch occurs at such a high rate, and effectively, that means only the bottom of your trench is being etched at a high rate. There will still, of course, be etching of your side walls, right? It's not perfect. The anisotropy factor can never be exactly 1, but at least it's much better than your purely chemical etching. Okay, so because, right, of course, your anisotropy factor, even with reactive ion etching, is not 1, but sometimes you really need it to be very close to 1. We really want very deep and narrow trenches, which requires higher anisotropic etch, right? So we have this idea of ion enhanced inhibitor etching, where the inhibitors basically are generated by the addition of certain gases into your plasma. So for example, if you add carbon containing gases, CHF3, C4H8, right, into your plasma, what happens is that under the bombardment of the ion in the plasma environment, it can, right, react, polymerize to form some sort of polymeric or carbonaceous layer, right? Polymer or carbonaceous layer, and this will coat on the surfaces, right, of your trench. Okay, it will coat on your side wall, but and also on your bottom. But the bottom is always being cleaned by your ion bombardment. Your ion bombardment ensures that your bottom surface, right, any polymer or carbonaceous inhibitors formed on the bottom surface of your trench is removed by the constant arrival of argon ions that can somewhat clean it, right? So effectively, your inhibitors only coat or mainly coat on your side walls, thus protecting your side walls even more from etch. So effectively, this is able to constrain your etching on the bottom surface and ensure very high anisotropy etch, right? Very high aspect ratio trenches can be defined. Okay, and we can tune actually the ratio of your etching chemically active, right, etching gas and your the gas which generates the inhibitors, right? We can tune that gas ratio to tune the kind of slope that you eventually achieve, right? Whether you want very close to 90 degrees or like having a slight angle to it, things like that. Yeah. So that is actually the impact of your chemistry on this etch process, right? So for example, right, if we use, let's say, a fluorocarbon for your etching gas, use a fluorocarbon for etching gas. Okay, when you have a low fluorine ratio, right, SiO2 is etched at a much higher rate than nitride and silicon because SiO2 is more sensitive to fluorine etch. It is more easily etched by, let's say, a low fluorine concentration. However, when you have a high fluorine concentration, like CF4, so every molecule has like every carbon atom, right, has 4, right, fluorine atoms connected to it. So you can say that this is a high fluorine concentration or a high fluorine to carbon ratio. We see that both silicon and nitride and SiO2 all get etched very quickly, right? And so this is poor selectivity. So for example, let's say you are using nitride to mask the areas where you want to etch the oxide below, right? And nitride is being used to mask the areas where you do not want to etch, of course. Then you do not want to have to be in this regime where nitride is etched as fast as silicon. So silicon dioxide, yeah, it's your oxide. So because when you're in this regime, your nitride will not act as a very good mask for your etching of your oxide layer below. Okay. So that's why we need to choose your ratio of fluorine to carbon to obtain the best kind of etching selectivity. Okay, and the second idea is that the diluent gases that you add in, right, that maybe do not participate directly in the chemical reaction, right, also affects your etching chemistry and your eventual etching performance. For example, if you add hydrogen gas as a diluent gas, right, effectively it pushes like the behavior of your fluorocarbons more towards polymer deposition. So your etching rate will be slower, but your profiles will be more anisotropic. However, if you add oxygen gas discourages your polymer deposition and encourages your reactive fluorine radical to be produced. So more reactive fluorine radicals will be produced, etching will be faster, but will be less anisotropic. Okay, So we can this is important aspect to consider in your etching chemistry. And here's a good like image, for example. So if we increase, right, so let's say maybe you are an engineer, then you see this diagram. Wow, this is not good, because your etching profile, there's like the we call this a bowing effect, right? So it's basically a not a good clean isotropic etch. There's poor protection of the sidewall, poor protection of the sidewall. So we may think, okay, how to protect my sidewall? I reduce my concentration of the reactive gas that produce the most fluorine radicals, and I increase the ratio of my fluorocarbon that can produce your polymer deposition on the sidewall. So now the sidewall is more protected, and my etch rate maybe is a bit slower, and indeed, right, it produces more anisotropic, nicer kind of etch profile that is more towards what we want to achieve. Right. So now I'll cover this idea of what will be the case where if we want a very, very, very high aspect ratio trench, we may need to implement this idea of a Bosch process. So it's like alternating kind of cycle. So we have an alternating cycle. We first pump in, let's say, your the gas where there's able to etch your material. So you first pump in your etching gas, right? So there's a bit of etching downwards. Then we pump in your passivation gas. So the gas that will form your polymer deposition to protect the sidewall. Then it will coat the surface. Okay, it will coat the surface with your polymer. Then we of course we let some ion bombardment to occur to remove the passivation, to remove the polymer that's on the bottom surface. Then we pump in the etching gas once again. So there's a alternating steps of sidewall protection, right? Etching, sidewall protection, etching, and all that. So we can get very, very, very vertical slopes. It's etched down like very vertically, right, in sequential steps. Okay. However, the problem is that we tend to get this kind of scalloped shape because there's this alternating etch and deposition cycle. So that in the end, there's also some alternating patterns in our profile. Okay. So we can also, right, go back to our usual way, which is not the Bosch process, which is a single step process with both your polymer inhibitor kind of gas and your etching gas. However, this generally slows down the etch rate as well. Okay, because now your etching and your polymer deposition is occurring together. Okay, so let's take a look at some common plasma etching recipe. Let's say if you want to etch silicon, you tend to use fluorine-based species, right, or like basically a halogen, right, based species, and your byproducts form are all volatile. For oxide or nitride, right, we can use a fluoride-based etch, right. For aluminium, right, we tend to use chlorine-based, right, chlorine-based, because AlCl3 and its dimer Al2Cl6 are volatile and all that. And photoresist, right, we for organic species, we like to use the oxygen-rich environment to produce your CO2 and your H2O. Okay, so this is my last slide, no, second last slide, but basically is to explain, right, these two configurations that plasma etching can occur in. So the case where we have always been explaining just now is a capacitively coupled plasma system where the bias that kind of maintains your plasma is applied directly to your electrodes where your wafer is on, right? Your wafer will be on one of these electrodes, right? So the problem with this is that let's say you want to make your plasma more dense or higher in basically greater density of the plasma. So you need to ionize more species in your plasma. So we need to impose a higher power, higher bias. But what's the downside of this? The downside of this is that now your bias at your electrodes is greater also. Right? Electric field at your electrodes is greater also. So your ions will start to bombard your wafer at a much higher speed. That may not always be desirable because it can cause damage to areas where you don't want so high ion energy to be bombarding your wafer surface. So there's this idea of inductively coupled plasma system or ICP system where the power that maintains your plasma is not directly connected to your wafer. So we have a series of coils, let's say at the top of the machine, that generates the plasma and a separate bias that's applied to your wafer. So you can think of the power, the ICP power, over here to be generating the plasma and controlling the ion density, the ionization efficiency, ionization density of a plasma. And the bias connected to your wafer below to be controlling the energy of the ion bombardment, because it controls the electric field that exists at the wafer surface. So it kind of separates plasma generation from the bias at the wafer. So effectively you can maintain a high density plasma by having a very high ICP power, but your ion bombardment on your wafer is still not very high energy, because let's say your bias power connected to your wafer is kept low, right? So what is the good part of this is that by using high ICP power, I can generate sufficiently dense plasma at lower gas pressures. So that means my gas in the plasma, right, can be at a lower pressure. And when there's a lower pressure, right, in the plasma, my uh, the mean free path for ion movement through the plasma is longer. Because you can think of it in this way. When the plasma pressure is lower, that means there are less gas particles per unit volume, right? That's why the pressure is lower in the plasma. So when there's less gas particles per unit volume, right, my ions can move through a longer distance before encountering and colliding off a gas molecule, right? So when there's a longer mean free path, my ions will be less scattered to random directions, and it can fall on the wafer more vertically. And this is important for directional etch, because remember that the whole idea of directional etch is because your bottom surface of your trench receives ion bombardment while your side walls don't, right? That's the principle. So if your ions come in more vertically downwards, of course your etching will be more directional, versus if, right, let's say you have a high pressure that's required resulting in a short mean free path and your ions get scattered into all directions. That means your side wall also will have some ion bombardment, because the ions are also arriving on the wafer at all sorts of strange angles, right? So that is not good for directional etching. Okay, so this is just one of the various reasons why ICP plasma is very important and is commonly used in reactive ion etching. And so last thing I'll cover, is it the last thing? Yeah, last thing I'll cover is atomic layer etching. So atomic layer etching is very interesting. So we want to etch one layer at a time. So you may or may not have heard of the idea of atomic layer deposition, right? So this is like the etching counterpart of atomic layer deposition. So how it works is that first, chlorine gas is pumped to your wafer surface. Then after that, the chamber is flushed, so that only the chlorine that binds to your wafer surface is maintained. So only one layer of chlorine, in a sense, is adsorbed on your wafer surface. The rest will be flushed away. Then after that, there's a gentle bombardment of the wafer with ions. And so the top layer of, let's say, silicon atoms that have binded to the chlorine atoms are more easily to be removed by the gentle ion bombardment, right? Because the formation of the Si-Cl bonds during the binding process weakens the Si-Si bond in the material. However, only the first layer, right, is susceptible to the effect, because only the first layer of atoms had binded themselves to the chlorine atoms. So it must be gentle. The gentle bombardment of the argon ions will only remove the first layer of the chlorine atoms. Of the silicon atoms from a silicon wafer. And so this process is then repeated to remove layer after layer after layer of the silicon, achieving, right, a form of etch that can be done atomic layer by atomic layer. Okay, so in this video, I've covered this whole idea of etching, dry etching, also known as plasma etching, right? And in the next video, I will probably cover physical vapor deposition, also known as sputtering deposition. I will also cover electrochemical plating, and because of the close link between electrochemical plating and chemical mechanical polishing in the Damascene process in the back end of line, I will also cover CMP in the same video. Okay, so this is the end of this video. I hope it was educational, that you all learned something from it, and see you in the next video.